Have you ever looked up at a starry night and felt a sense of wonder, only to realize that some of the most breathtaking patterns above aren't just beautiful? They're profoundly mysterious, defying everything we think we know about the universe. What if I told you that hidden among the constellations and cosmic clouds are strange formations, alignments, and symmetries that scientists still can't fully explain? These aren't just random arrangements, they're cosmic anomalies that challenge the very foundations of astronomy and physics, inviting us to reconsider our understanding of reality itself. From inexplicable gravitational forces pulling entire galaxies toward unseen structures, to eerie geometric shapes spinning on distant planets, the cosmos is filled with patterns that push the boundaries of human knowledge. And the most astonishing part, many of these mysteries are visible right above us, waiting to be unraveled. In this video, we're setting off on a journey to explore 25 of the most unusual cosmic patterns ever discovered, each one a celestial puzzle that has left researchers intrigued, inspired, and at times completely baffled. We'll dive into the origins of these phenomena, from the vast scales of galactic superstructures to the intricate mechanics of planetary weather systems. We'll examine what these patterns imply about the nature of dark matter, the possibility of multiverses, and even the fundamental laws that govern space and time. Along the way, we'll confront mind-bending questions. Could some of these formations hint at unknown physics? Or might they point toward something even more extraordinary, just beyond the edge of our current understanding? Whether you're an experienced stargazer or someone who simply loves to ponder the grandeur of the universe, this exploration promises to transform how you see the night sky and reality itself. So settle in, open your mind, and get ready to look upward with new eyes. Our journey begins with a gravitational mystery so powerful it's tugging our entire galaxy toward it. Hidden behind a veil of cosmic dust, the first of many wonders that remind us the universe is far stranger and more beautiful than we ever imagined. Picture a region of space so immense and so gravitationally powerful that it is pulling our entire galaxy, along with countless others, toward it at a breathtaking speed of over 14 million miles per hour. This isn't science fiction, it's a very real cosmic mystery known as the Great Attractor. For decades, astronomers were puzzled by this peculiar motion of our local galactic group, a motion that couldn't be explained by the visible matter we could see. The source of this tremendous pull was hidden from our view, lying in a direction of the sky obscured by the dense stars, gas, and dust of the Milky Way's central bulge, an area astronomers poetically call the zone of avoidance. It's like trying to see a distant city through a thick, impenetrable fog. We knew something massive was there, exerting its influence, but its true nature was completely concealed. Through persistent observation using wavelengths of light that can pierce through that cosmic dust like infrared and radio waves, we've begun to lift the veil. We now believe the Great Attractor is not a single, incomprehensible object, but rather an enormous concentration of mass, a gravitational focal point known as the Laniakea supercluster, of which our own Milky Way is merely a drifting suburb. This supercluster is a vast network of hundreds of thousands of galaxies, all bound together by gravity, and we are flowing toward its dense center. Yet, even with this identification, the mystery deepens. The sheer amount of visible matter in this supercluster still doesn't fully account for the immense gravitational force we experience. This strongly suggests that the true architect of this motion is the invisible hand of dark matter, the elusive substance that makes up the majority of the universe's mass but refuses to interact with light. This gravitational anomaly fundamentally challenges our perception of the cosmos. It reveals that the universe is not uniform. It has an architecture, a topography of immense gravity wells and vast empty voids on a scale that is almost impossible to comprehend. The Great Attractor forces us to acknowledge that what we see with our telescopes is only a fraction of the story. The most powerful forces shaping our cosmic journey are exerted by structures we can barely detect, prompting a profound and humbling question. If something this massive could remain hidden in plain sight for so long, what other colossal, invisible patterns are waiting to be discovered in the deep dark between the stars? Now, if the Great Attractor shows us the power of hidden mass, the second pattern reveals a mystery of alignment on a truly staggering scale. Imagine looking out across billions of light years and discovering that the universe's most powerful beacons are not randomly placed, but seem to be coordinated, their rotational axes mysteriously aligned like compass needles, all pointing in the same direction. This is the baffling case of quasars. These are not stars, they are the phenomenally energetic cores of distant galaxies, where supermassive black holes are actively feeding, and in the process, they become the brightest, most persistent objects in the entire cosmos. Their light has traveled for eons to reach us, and in studying that light, astronomers began to notice something that should be statistically impossible. Across volumes of space so vast they encompass hundreds of thousands of these brilliant objects, the spin axes of the quasars' central black holes, and by extension the immense jets of plasma they often shoot out, appear to be aligned with each other. They are not pointing in random directions as our standard models of the universe would predict. Instead, they show a surprising degree of coherence, a preferred orientation that stretches across structures like the cosmic web itself. It's as if you threw a million needles into the air and they all landed pointing north. This isn't just a local oddity. This alignment spans distances so enormous that not even light has had enough time since the Big Bang for information to travel between these quasars and coordinate their behavior. They are, by all known laws of physics, causally disconnected. They shouldn't be able to influence each other, and yet they seem to be. This presents a monumental challenge to cosmology. How do you explain this? One compelling, if mind-bending, theory points to cosmic strings. These are not strings in the everyday sense, but hypothetical, ultra-dense defects in the fabric of spacetime itself, relics from the universe's earliest, most violent moments of expansion. Think of them as cracks or wrinkles frozen into the fundamental structure of reality. If they exist, these cosmic strings could have unimaginable mass and would exert a profound influence on the spacetime around them, potentially dictating the alignment of matter and energy across cosmic distances, acting as a guiding framework upon which galaxies and their black holes formed. Another possibility is that this alignment is a fossil, a remnant from the primordial universe, imprinted during a period of rapid inflation. It could be a clue that the initial conditions of the cosmos were not perfectly uniform and isotropic as we often assume, but had some inherent spin or polarization that got locked into place as the universe expanded, a ghost of order from the very first moments of time. Of course, some scientists argue this could all be a trick of perspective, a vast statistical fluke that our observations have somehow caught. But as more data rolls in from powerful telescopes, the evidence for this large-scale alignment only grows stronger, making the fluke explanation less and less probable. The implications are truly profound. If this pattern is real and not an illusion, it means our understanding of the universe on the largest scales is incomplete. It suggests there are forces or structures at work that we have not yet begun to comprehend, a hidden architecture to reality that orchestrates the universe in ways we are only starting to glimpse. It forces us to question whether the cosmos is truly random, or if it possesses a deep, underlying order that connects the farthest reaches of space in a way we never thought possible. Leaving behind the vast alignments of quasars spanning the cosmos, we find an equally stunning but far more intimate geometric wonder right here in our own solar system. At Saturn's North Pole, a storm of breathtaking precision rages, a nearly perfect hexagon, each side wider than our entire planet, tracing the outline of a colossal atmospheric vortex. This isn't a fleeting cloud formation, it's a permanent feature, a six-sided hurricane that has been churning with metronomic stability for decades, and likely for centuries. When the Voyager probes first glimpsed it in the 1980s, scientists were utterly baffled. Weather, as we understand it on Earth, is chaotic and fluid, producing swirling cyclones and meandering jet streams, but never rigid, geometric shapes with razor-sharp, 60-degree angles that persist season after season. This is a pattern that belongs more in a geometry textbook than in a planet's atmosphere. The scale of this phenomenon is almost impossible to grasp. If this hexagon were placed over Earth, it would stretch from the North Pole down to deep into the mid-latitudes, enveloping continents in its geometric embrace. And it's not just a static drawing in the clouds, it's a dynamic, powerful jet stream with winds screaming along its walls at over 300 miles per hour, carrying with it a deep-rooted weather system that plunges far down into the planet's gaseous interior. The mystery isn't just that it exists, but that it remains so incredibly stable. On our world, even the most powerful storms dissipate within weeks. Saturn's hexagon has outlasted generations of human observation without so much as wavering in its perfect form. So how does a gas giant forge such an impossible shape? Planetary scientists believe the secret lies in the unique conditions of Saturn's atmosphere, a deep, fluid envelope of hydrogen and helium without a solid surface to disrupt the flow. In laboratory experiments, when a fluid is placed in a circular container and rotated at different speeds, it can sometimes self-organize into stable polygonal shapes, including hexagons. The leading theory suggests that deep within Saturn, a colossal eastward-flowing jet stream at the North Pole encounters slower-moving surrounding gases. This difference in velocity creates a shear zone, and under the right conditions of rotation and density, this shear can become organized into standing waves that manifest as the hexagon's straight sides. It's a natural product of fluid dynamics, but on a planetary scale we rarely get to witness. Yet, even this compelling explanation feels incomplete. The stunning precision and longevity of the hexagon suggest there are deeper layers to Saturn's atmospheric mechanics that we have yet to unravel, perhaps involving hidden energy sources or interactions with the planet's internal magnetic field. This celestial polygon is more than just a curiosity. It's a profound reminder that the laws of physics can manifest in astonishingly beautiful and unexpected ways. It challenges our Earth-centric intuition and shows us that nature's repertoire of patterns is far more diverse and creative than we could ever imagine from our own planetary experience. As we marvel at this geometric storm, we are reminded that some of the universe's greatest puzzles are not always found in the distant, ancient cosmos, but are sometimes spinning gracefully right next door, waiting for us to decipher their elegant, swirling code. But if Saturn's hexagon shows us the strange beauty of order within our own solar system, the next pattern takes us to the very edge of the observable universe, to a relic of creation itself, and it's here we find a profound chill that shouldn't exist. To understand this, we need to look at the oldest light in the cosmos, the cosmic microwave background, or CMB. This is the faint thermal radiation that fills every corner of space, the cooled remnant of the primordial fireball of the Big Bang. It's the universe's baby picture, a snapshot taken when it was just 380,000 years old, and it is remarkably uniform, a nearly perfect blanket of microwave heat with only tiny, random variations in temperature. These tiny fluctuations are the seeds from which all cosmic structure galaxies, clusters, and the great cosmic web eventually grew. So when astronomers mapped this background, they expected to see a gentle, random tapestry of warm and cool spots. What they did not expect to find was a colossal cold spot so vast and so profoundly cold that it defies easy explanation. This anomaly, known officially as the CMB Cold Spot, is not just a little bit cooler than its surroundings. It is a staggering void of cold in the afterglow, a region nearly 1 billion light-years across where the temperature dips significantly lower than our standard models of the universe can account for. It's as if you were feeling the warmth of a campfire and suddenly your hand passed over a patch of air that was inexplicably, deeply cold. The sheer scale of this spot is what makes it so problematic. If it were a real physical structure in the universe, like a giant void, a cosmic desert with very few galaxies, then the light passing through it would lose energy as it expands with the universe, creating a cold imprint in the CMB through a process known as the integrated Sachs-Wolf effect. Some surveys have indeed found evidence of a sparse supervoid in that general direction, but the problem is, this void isn't nearly large enough or empty enough to explain the profound cold we see. The numbers simply don't add up. The observed void can only account for a fraction of the temperature drop. This discrepancy has led to some of the most extraordinary hypotheses in modern cosmology. One breathtaking possibility is that the cold spot is evidence of a cosmic collision, a bruise left on our universe from an impact with another universe in the vast multiverse. In this mind-bending scenario, the cold spot could be the signature of a bubble universe colliding with our own during the early period of inflation, a titanic event that would have drained energy from that region of space, leaving it permanently colder. It's a theory that stretches the limits of scientific imagination, suggesting that our cosmos is not alone but is one of many in a greater metaphysical reality. Of course, the more conservative explanation is that this is simply a statistical fluke, a rare and massive random fluctuation in the CMB that, while incredibly improbable, isn't impossible. Our universe is vast and improbable things can happen, yet the cold spot stands out even after rigorous analysis, remaining a stubborn outlier that refuses to be explained away. This cold patch in the sky is more than just a data point. It is a direct challenge to the standard model of cosmology, known as lambda CDM. This model has been incredibly successful at explaining the large-scale structure and evolution of the universe, but the cold spot is a glaring anomaly it struggles to digest. It forces astronomers to confront the limits of their theories and their observations, a humbling reminder that our cosmic map still has areas marked "Here be dragons." Whether it's a window into the multiverse or simply a rare cosmic oddity, the cold spot underscores a powerful truth. The universe is capable of producing patterns so vast and so strange that they compel us to question the very framework of our reality. And from this ancient, frozen imprint on the dawn of time, we now turn to a pattern that is the polar opposite. Not a cold, silent relic, but a brilliant, energetic, and repeating signal from the distant universe that arrives with the precision of a clock. From the ancient, frozen silence of the cosmic microwave background, we now turn to a phenomenon that is its energetic opposite. Brilliant, millisecond-long shrieks of radio energy that erupt across the cosmos with the startling regularity of a ticking clock. These are fast radio bursts, or FRB, and they represent one of the most electrifying mysteries in modern astronomy. Imagine a flash of radio waves so powerful that in a fraction of a second, it releases more energy than our sun does in 80 years. For a long time, astronomers believed these were one-off cataclysmic events, the final death cries of stars being shredded by black holes or the collisions of incredibly dense neutron stars. The sheer brevity and power of these signals pointed to a violent, singular origin. That is, until we found one that came back. The discovery of a repeating FRB shattered the cataclysm model entirely. Here was a source billions of light years away that would fire off these tremendous bursts not just once, but again and again. And as we kept listening to this and other repeating sources, an even more bizarre pattern emerged, a precise periodicity. One of the most famous repeaters, known as FRB 180,916, exhibits a dramatic 16-day cycle. For 4 days, it might fire off several bursts an hour, and then it falls completely silent for the next 12 days, only to start the entire process over again with metronomic reliability. Another source has a cycle lasting nearly 160 days. This isn't the behavior of a random explosion. This is the signature of a cosmic engine, an astrophysical machine operating on a strict, predictable schedule. This incredible regularity immediately narrows down the list of potential culprits and pushes our theories into fascinating territory. The prime suspect for many of these bursts is a type of neutron star called a magnetar. These are the universe's ultimate magnets, stellar corpses with magnetic fields so intense they could erase a credit card from halfway to the moon. One leading theory suggests that a magnetar with a rocky, planetary companion in a highly elliptical orbit could be the source of the periodic burst. As the magnetar swings close to its companion, the tremendous gravitational tides could crack its crust, releasing flares of energy that we see as FRBs. Then, as it moves away on its long orbit, the activity ceases, creating the long silent period. This elegantly explains the clockwork nature, tying it to a simple orbital mechanic. But the precision of these timers is so exact that it inevitably leads to more speculative and certainly more thrilling possibilities. Could such a consistent, organized pattern be the product of an advanced intelligence? The idea of it being a beacon or some form of interstellar communication, while firmly in the realm of last resort explanations, is a testament to how truly perplexing these signals are. They force us to consider every conceivable option. The reality is likely a spectacularly violent natural process, but the mere fact that the extraterrestrial hypothesis is even discussed in serious scientific circles highlights how much these bursts defy our current understanding. What makes repeating FRBs so revolutionary is that they are not just mysterious signals. They are potentially the most powerful tools in cosmology since the discovery of the redshift. Because these radio waves travel across such immense distances, they interact with the tenuous fog of free electrons that floats between galaxies. This interaction leaves a specific fingerprint on the burst, allowing astronomers to measure the total amount of material the signal passed through on its way to us. Essentially, each FRB is a cosmic dipstick measuring the density of the universe along its path. By collecting enough of these signals, we could finally map the universe's missing baryonic matter, the ordinary atoms that theories say should be there but have eluded our telescopes. This would allow us to weigh the cosmic web itself and provide an entirely new, independent test for our models of the universe's structure and expansion. So, in these fleeting, rhythmic bursts, we find a beautiful duality. They are both a profound mystery that challenges the limits of astrophysics and a potential key that could unlock the secrets of the cosmos's large-scale structure. They are cosmic clocks, yes, but they are also cosmic cartographers, and their persistent, enigmatic ticking is slowly but surely drawing us a new map of the universe. This intricate dance of precise timing and raw power in the radio spectrum finds a surprising visual echo in the grandest structures of all, where another form of cosmic order unfolds with mathematical elegance, the majestic spiral arms of galaxies. This breathtaking spiral architecture we see in galaxies like our own Milky Way isn't just a random swirl of stars. It often follows a precise mathematical pattern known as the golden ratio, a number approximately equal to 1.618 that has fascinated artists, architects, and mathematicians for millennia. This ratio, intimately linked to the Fibonacci sequence where each number is the sum of the two preceding ones, appears throughout nature on Earth, in the arrangement of sunflower seeds, the spiral of a nautilus shell, and the branching of trees. To find this same mathematical principle governing structures 100,000 light-years across is nothing short of awe-inspiring. It suggests a universal language of form and growth, a common thread weaving through the fabric of reality from the microscopic to the cosmic. When we look at a grand design spiral galaxy, its arms don't just curve, they unwind in a logarithmic spiral, meaning the distance between each turn of the arm increases by a constant factor, a pattern that can be perfectly described by this ancient ratio. The immediate and perhaps romantic question is, why is this a profound coincidence, a simple consequence of physical laws playing out? Or does it point to something deeper, a fundamental constant governing self-organization across the universe? The answer, while less mystical, is no less fascinating. This spiral pattern is primarily a density wave, a kind of gravitational traffic jam propagating through the galactic disk. As stars and gas clouds orbit the galactic center, they don't move at a uniform speed. Their orbital period varies with distance. This differential rotation would naturally tend to wind any initial structure into a tight spiral over time. However, the persistence and clarity of these spirals indicate a self-sustaining process. The wave itself creates regions of higher density, which in turn amplify the gravitational pull that sustains the wave. It's a perfect feedback loop of gravity and motion, and the most stable, efficient, and energetically favorable pattern that emerges from this chaotic dance is often one that aligns with the golden ratio. It represents a state of dynamic equilibrium, the universe finding an elegant solution to organizing immense amounts of matter and energy. Studying these spirals is far more than an aesthetic pursuit. It is crucial for unlocking the secrets of galaxy formation and the invisible hand of dark matter. The rotation speed of a galaxy's arms doesn't follow the expected drop-off predicted by the visible mass alone. Stars on the outer edges orbit just as fast as those near the center. This was one of the first and strongest pieces of evidence for dark matter. The graceful shape of the spiral is therefore painted not just by the stars we see, but by the gravitational influence of the vast, invisible halo of dark matter in which the entire galaxy is embedded. The specific pitch and tightness of the spiral arms are direct traces of this underlying gravitational potential. By meticulously mapping these celestial pinwheels, astronomers can effectively weigh the galaxy and chart the distribution of its dominant but unseen component, using the beautiful mathematical order of the spiral as a tool to probe the deepest shadows of the cosmos. This discovery connects the human scale to the galactic in a deeply meaningful way. The same ratio that defines the proportions of the Parthenon and the Mona Lisa also shapes the whirlpool of stars we call home. It hints that the universe may operate on a set of elegant, mathematical principles that manifest at every scale, from the growth of a fern frond to the birth of a galaxy. This isn't necessarily a guided design, but rather a testament to the universal laws of physics, gravity, angular momentum, and dynamics that naturally give rise to efficient and often beautiful forms. The spiral galaxy, in its magnificent Fibonacci curve, stands as a powerful symbol of this cosmic order, a reminder that even in the vast, seemingly chaotic depths of space, there is an underlying pattern, a rhythm, and a profound mathematical beauty waiting to be decoded. And if this pattern shows us the elegant order within individual galaxies, it makes us wonder what breathtaking architecture emerges when we zoom out to see how these galaxies themselves are arranged on the largest canvas imaginable. And if the spiral arms of a galaxy represent a beautiful, localized order, then the cosmic web is the universe's grandest architectural blueprint, a vast, intricate lattice of dark matter and galaxies stretching across billions of light years, connecting everything in a delicate, filamentary network. This is not how we once imagined the cosmos. It is not a random scattering of islands in a void. Instead, the largest simulations and galaxy surveys, like the Sloan Digital Sky Survey, reveal a structure of breathtaking complexity and scale, a cosmic spiderweb where galaxies cluster like dewdrops at the intersections of silken threads. These filaments are the superhighways of the universe, the great scaffolding upon which all visible matter is arranged, and they fundamentally challenge our perception of cosmic randomness, revealing a deep, gravitational order that has been evolving for nearly 14 billion years. This magnificent structure is primarily the work of dark matter. In the early universe, tiny quantum fluctuations were amplified by the rapid inflation of space, creating minute differences in density. Over eons, the relentless pull of gravity acted on these seeds with dark matter, which feels gravity but not light leading the way. It collapsed first into a web-like network of sheets and filaments, creating a gravitational skeleton. Ordinary matter, the atoms that make up stars, planets, and us, was then simply pulled along for the ride, flowing into these gravitational valleys and pooling at the densest nodes, where we now find immense galaxy clusters. The cosmic web is therefore a direct imprint of the primordial universe, a fossilized record of its initial conditions, magnified by time and gravity to a scale almost beyond human comprehension. Yet, for all its grandeur, this web remains elusive. We cannot see the dark matter filaments directly. Instead, we map them indirectly by charting the precise three-dimensional positions of millions of galaxies, revealing the empty voids and the dense walls between them. We also use a phenomenon called gravitational lensing, where the mass of a filament bends the light from galaxies behind it, acting as a cosmic magnifying glass that allows us to literally weigh these invisible structures. What we've found is that the filaments are not empty. They are traced by a faint, diffuse ocean of incredibly hot gas known as the WIM, the warm hot intergalactic medium. This is the universe's missing baryonic matter, a long-sought reservoir of ordinary atoms that had evaded detection for decades, now found hiding in the faint glow within the web strands. The existence and precise structure of this cosmic web also provide our most powerful tools for understanding dark energy, the mysterious force accelerating the universe's expansion. By measuring how the web has evolved over cosmic time, how filaments have thickened and clusters have grown, cosmologists can test different models of dark energy. A stronger dark energy would have acted more quickly to pull the universe apart, suppressing the growth of this large-scale structure. The fact that we see such a well-developed web, with filaments that have been in place for billions of years, helps us constrain the nature and strength of this enigmatic component of the cosmos. It is a cosmic balancing act between the relentless pull of gravity-building structure and the repulsive push of dark energy trying to tear it apart. So the cosmic web is far more than a pretty pattern. It is the ultimate expression of gravity's creative power and the central playing field for the greatest drama in modern cosmology. It connects the very large to the very old, tying the fate of galaxy clusters to the first whispers of the Big Bang. But just as we begin to appreciate this vast, orderly architecture, a new and deeply puzzling pattern emerges on a slightly smaller scale, one that seems to defy the very rules that built the web in the first place. For when we look at the satellites dancing around galaxies like our own Milky Way, we find they are not moving randomly within this grand design. Instead, they are moving in eerie, synchronized harmony, a coordination that our current understanding of the cosmic web and dark matter struggles to explain. This cosmic choreography presents a direct and serious challenge to our prevailing model of cosmology, known as lambda cold dark matter. This model has been wildly successful at explaining the universe on its largest scales, predicting the cosmic web and the distribution of galaxy clusters with remarkable accuracy. However, it makes a very specific prediction about satellite galaxies. They should be arranged in a roughly spherical, random swarm around their host, like bees buzzing chaotically around a hive. This is because the massive, extended dark matter halo of a galaxy like the Milky Way is thought to be fairly spherical, and the satellites, which are believed to be the surviving remnants of the first small galaxies that merged to form the larger one, should be orbiting in all different directions, tracing the gravitational contours of this invisible sphere. The discovery of these thin, co-rotating planes of satellites is like finding all those bees flying in a single, neat, rotating disk, a configuration that the standard model struggles to produce in its simulations without appearing contrived or statistically unlikely. This discrepancy has forced astronomers to consider some radical alternatives. One possibility is that our understanding of dark matter itself is incomplete. Perhaps dark matter is not entirely cold and collisionless, but has some other property that allows it to interact in ways we haven't accounted for, leading to the formation of these vast, coherent structures. An even more profound suggestion is that we might need to modify our theory of gravity itself. Theories like modified Newtonian dynamics, or MUND, propose that gravity behaves differently at very low accelerations, like those found in the outskirts of galaxies. Intriguingly, some versions of MUND naturally predict that satellite galaxies would form in a single plane, potentially offering a more elegant solution to this puzzle without invoking dark matter at all. However, MUND has its own set of challenges explaining other cosmic phenomena, leaving the scientific community deeply divided on the best path forward. A more conventional, yet still fascinating, explanation lies in the recent history of our galactic neighborhood. We know that the Milky Way and Andromeda are on a collision course, destined to merge in billions of years. It's possible that the synchronized motion of our satellites is not a primordial feature but a relatively recent development, orchestrated by the gravitational influence of this impending colossal encounter. Alternatively, the satellites we see today might not be a random sample. They could be a group of objects that were all accreted together in a single, massive event billions of years ago, a family of galaxies that have maintained their shared motion ever since, like a school of fish swimming in unison through the cosmic ocean. Each of these explanations carries its own implications and its own set of unanswered questions, turning what was once a minor detail of galactic structure into a major frontier in our quest to understand the fundamental forces shaping the cosmos. This celestial synchrony, whether a ghostly echo of a long-ago merger or a signpost pointing toward new physics, serves as a powerful reminder that our models of the universe are always works in progress. It demonstrates that even the most well-established theories must be continually tested against the evidence, and that sometimes the most revealing clues come from the subtle, coordinated dance of the smallest galaxies around our own. This very coordination, this suggestion of a larger, influencing structure, naturally leads our inquiry toward an even more fundamental measurement of the cosmos, one that should be universal and unwavering, but is instead revealing a troubling and growing disagreement that strikes at the very heart of modern cosmology. This precise measurement of the cosmos's current growth rate is known as the Hubble constant, and for decades, astronomers have been refining their methods to pin down its exact value. The tension arises because two of our most trusted yet fundamentally different methods are now returning answers that are undeniably, stubbornly inconsistent. The first approach looks into the deep past, using the cosmic microwave background as a cosmic ruler. By studying the subtle fluctuations in this ancient light, we can extrapolate forward through the entire history of the universe, using our well-tested standard model of cosmology, lambda CDM, to predict what the expansion rate should be right now. This method, championed by the Planck satellite, gives us a very specific value. The second approach builds a distance ladder in the local universe, measuring the expansion rate directly by observing how fast galaxies are moving away from us. This involves using pulsating stars called Cepheid variables and certain types of supernova as standard candles, objects whose intrinsic brightness we know, allowing us to calculate their distance accurately. By comparing their distance to how fast they are receding, we get a direct measurement of the Hubble constant. Teams using the Hubble Space Telescope and other observatories have meticulously refined this technique, and their result is consistently higher than the prediction from the early universe. The difference is not a small margin of error. It's a significant gap that has only widened as our measurements have become more precise. It's as if you calculated how fast a tree should be growing based on its seed and the nutrients in the soil, and then you directly measured the tree's growth a year later, only to find it's growing noticeably faster than your prediction. One of these methods must be wrong, or more intriguingly, our understanding of the physics connecting the early universe to the present day is incomplete. This isn't just a minor academic disagreement, it's a potential crisis for cosmology because it suggests a flaw in our standard model. The lambda CDM model has been incredibly successful, but the Hubble tension is a crack in its foundation. Scientists are now exploring extraordinary possibilities to explain this discrepancy. Could dark energy, the mysterious force accelerating the expansion, not be constant as we assumed? Perhaps it is evolving, growing stronger over time. Or maybe there is an entirely new type of dark radiation or an unknown subatomic particle that was present in the early universe and altered its evolution. Some have even proposed more radical ideas, like the notion that our galaxy sits in a giant cosmic void, a region of lower density that could locally affect our measurements, though this is generally considered a long shot. Each proposed solution tries to tweak the physics just enough to make the early universe prediction align with the local measurement, but so far, no fix has gained widespread acceptance. The tension persists, a nagging reminder that for all our knowledge, the universe still holds profound secrets about its own fundamental workings. Resolving the Hubble tension is perhaps the single most important goal in observational cosmology today. New missions like the James Webb Space Telescope are now joining the effort, using its powerful infrared vision to get a clearer look at the Cepheid variables and supernova in the distance ladder, checking for any hidden systematic errors that might be skewing the results. At the same time, entirely new techniques are being developed, such as using the gravitational waves from merging neutron stars as standard sirens to provide a completely independent measure of the expansion rate. The outcome of this endeavor will be revolutionary. If the tension is confirmed and our model is indeed broken, we will be forced into a new cosmological paradigm, one that likely includes new physics beyond our current understanding. This wouldn't be a failure of science, but a triumph, a demonstration that by paying close attention to the data, even when it's inconvenient, we are pushed toward a deeper and more complete truth about the cosmos. From this grand, fundamental conflict over the fate of the entire universe, we now turn our gaze to a single, specific star, a peculiar flicker of light that captured the world's imagination and presented a mystery on a much more intimate, but no less profound, scale. While the Hubble tension represents a conflict in our fundamental understanding of the entire cosmos, the mystery of Boyajian star brings the search for answers down to a single, twinkling point of light. Officially catalogued as KIC 8,462,852, this otherwise ordinary star located about 1,400 light-years away in the constellation Cygnus became an instant celebrity in 2015, earning the nickname Tabby's Star after its discoverer, astronomer Tabitha Boyajian. What made it famous was not what it was, but what it did, or more accurately, what passed in front of it. The Kepler Space Telescope, designed to find planets by the telltale, periodic dimming they cause when crossing their star's face, observed this star doing something utterly bizarre. Instead of the gentle, predictable, less than 1% dip of a planet, KIC 8,462,852 experienced dramatic, irregular plunges in brightness. On multiple occasions, its light output dropped by a staggering 22%. To put that in perspective, if a Jupiter-sized planet, the largest in our solar system, were to pass in front of this star, it would block only about 1% of its light. Whatever was causing this was not a planet. It was something colossal, something shapeless, and something that defied any easy classification. The initial data was so strange that it immediately sparked a firestorm of speculation within the scientific community and captured the public's imagination like few other astronomical discoveries. The most tantalizing, though least probable, hypothesis was that we were witnessing the construction of an alien megastructure. The concept, rooted in science fiction, involves a hypothetical Dyson sphere, a vast array of energy collecting satellites or panels built by an advanced civilization to harness the entire power output of its star. Such a structure, incomplete and irregular, could indeed cause the bizarre, aperiodic dimming patterns observed. While astronomers considered this the absolute last resort explanation, the very fact that it was discussed seriously in scientific papers highlighted just how unprecedented the signal was. It was a classic example of how a truly anomalous cosmic pattern can push us to consider every conceivable possibility. No matter how extraordinary, of course, the scientific pursuit focused on natural explanations, and the frontrunner for years was a colossal swarm of comets. The idea was that a family of exocomets, perhaps disturbed by a passing star, had been drawn in on extremely elongated orbits. As they swung close to Boyajian's star, they would break up, creating enormous clouds of dust and debris that could block a significant amount of starlight. The irregular timing of the dimming events could be explained by the chaotic nature of this disintegration. However, this theory faced its own hurdles. To create dips that deep, the amount of dust required was almost implausibly large, and such a violent cometary event should have generated a strong infrared signature from the warmed dust, which subsequent observations failed to detect in the expected amounts. Further long-term study revealed another baffling layer to the mystery. By analyzing historical photographic plates from the past century, astronomers found evidence that the star's overall brightness has also been gradually but steadily fading for over 100 years. This long-term dimming compounded the problem, making it even harder to find a single, elegant natural explanation that could account for both the sudden, deep dips and the century-long slow fade. Other theories have been proposed, including vast rings of dust-enshrouded asteroids, the aftermath of a cataclysmic planetary collision, or even the presence of a large, dark companion star surrounded by a complex debris disk that occasionally eclipses the main star. Each idea has its merits, but none yet provide a perfect, comprehensive fit for all the observed data. What makes Boyajian's star so enduringly significant is that it represents a new class of astronomical mystery. It's not that it disproves our theories of stars, rather, it reveals a gap in our imagination, showing us that there are physical processes or celestial architectures around stars that we simply haven't thought of yet. It stands as a powerful testament to the role of citizen science as well, as it was volunteers with the Planet Hunters project who first flagged the star's strange behavior in the Kepler data. This single, peculiar star has become a symbol of how modern astronomy works, a blend of automated telescopes, crowd-sourced analysis, and a willingness to follow the evidence, no matter how strange it leads. It reminds us that for all our cataloging of the heavens, the universe is still perfectly capable of throwing us a curveball, a single, flickering enigma that challenges us to think bigger and look closer. And as we ponder the strange, occluded architecture around this one star, it primes us to appreciate the opposite extreme on the cosmic scale, not a mysterious something, but a profound and puzzling nothing. After exploring the intricate, cloaked mysteries surrounding a single star, we now pull our perspective back to the very largest scales of the cosmos to confront not a presence, but a profound and startling absence. If the cosmic web is the universe's grand architectural skeleton, then the giant cosmic voids are the immense, empty chambers between its walls. These are not small, local pockets of emptiness. These are regions of space so vast they defy earthly comprehension, some stretching over 300 million light-years across. To traverse one of these voids at the speed of light would take a span of time longer than the entire existence of humanity on Earth. Within these colossal volumes, the expected bustling metropolises of galaxies are almost entirely absent. Instead of thousands of brilliant islands of stars, you might find only a handful of lonely, isolated galaxies drifting in a sea of near-total nothingness. This stark emptiness directly challenges one of cosmology's foundational principles, the assumption that on the largest scales, the universe is roughly uniform, with matter distributed evenly in every direction. The voids tell a different story, a narrative of extreme clumpiness where matter has gathered into the dense filaments and nodes of the cosmic web, leaving behind these breathtakingly empty deserts. The existence of these voids is not just a curiosity, it is a critical piece of the puzzle in understanding how the entire universe evolved. They are a direct prediction of the lambda cold dark matter model, the fingerprints of the initial conditions of the cosmos. The story begins with the faintest of whispers in the early universe, tiny quantum fluctuations in density that were amplified to cosmic proportions during the period of rapid inflation. Over billions of years, gravity acted as the great sculptor, relentlessly pulling matter from regions of lower density into regions of higher density. The voids are the regions that lost this gravitational tug of war. They are the low-pressure zones from which matter has steadily drained away, flowing into the web's filaments and clusters. As this evacuation progressed, the voids themselves expanded, becoming ever emptier and more pronounced. Their growth is not driven by an outward push, but by the relentless inward pull of the massive structures surrounding them. They are the sinkholes in the fabric of spacetime, defined not by what they contain, but by what has been taken from them. Studying these great nothings provides astronomers with a powerful, indirect way to probe the most mysterious components of our universe, dark matter and dark energy. The shape, size, and distribution of voids are exquisitely sensitive to the properties of dark energy, the force responsible for the accelerating expansion of the cosmos. A stronger dark energy would accelerate the expansion of these voids more quickly, affecting their growth and evolution over time. By meticulously mapping the sizes and shapes of thousands of voids, cosmologists can take the temperature of dark energy, constraining its strength and behavior in a way that complements other methods. Furthermore, the few galaxies that do reside within these voids are often fascinatingly peculiar. Isolated from the dense, violent environments of clusters, these void galaxies can evolve in relative peace, offering a unique laboratory to study galaxy formation in its most pristine and undisturbed state, free from the transformative collisions and interactions that are common elsewhere. This concept of a vast, structured emptiness is perhaps one of the most difficult cosmic patterns for the human mind to truly grasp. We are conditioned to think of space as simply the stage upon which the actors' stars, galaxies, and planets perform. But the voids force us to reimagine the stage itself. They are not a passive backdrop. They are active, dynamic entities that have grown and evolved alongside the glittering structures they border. They hold their own secrets about the flow of matter, the push of dark energy, and the ultimate fate of the cosmos. They remind us that the universe is a place of dramatic contrast, where magnificent splendor and profound emptiness exist side by side, each giving definition and meaning to the other. And from contemplating these immense regions of nothing, we now turn our gaze back to our own solar system, to a seemingly chaotic field of rocks where the universe has, against all odds, carved out a very different kind of pattern, one of unexpected and precise symmetry. But if the cosmic voids show us how gravity can sculpt vast emptiness, our own solar system reveals how the same force can carve out intricate patterns of absence within a seemingly chaotic field of rock. Between the orbits of Mars and Jupiter lies the asteroid belt, often depicted in popular culture as a dense, impassable obstacle course of tumbling boulders. The reality, however, is far more fascinating and orderly. This vast torus of primordial debris is mostly empty space. If you were to stand on one asteroid, you would likely not see another with the naked eye. Yet, within this sparse distribution, there exists a striking pattern of symmetrical gaps, regions where almost no asteroids are found at all. These are not physical gaps you could see, but statistical deserts revealed by meticulously mapping the orbits of hundreds of thousands of asteroids. The most famous of these are the Kirkwood gaps, named for 19th century astronomer Daniel Kirkwood, who first deduced their existence not by direct observation, but through the brilliant application of celestial mechanics and mathematics. These gaps are not random. They occur at specific, precise distances from the Sun where an asteroid's orbital period would form a simple, resonant fraction with that of Jupiter. For example, an asteroid in the most prominent gap would orbit the Sun exactly 3 times for every one orbit of Jupiter, a 3-to-1 resonance. This gravitational relationship with the solar system's largest planet is anything but harmonious for the asteroid. Imagine a child on a swing. If you give them a small push at the exact right moment in their swing cycle, you add energy and they go higher. But if you push at the wrong time, you disrupt their rhythm and slow them down. Jupiter acts as that relentless, powerful pusher. Its immense gravity gives a periodic tug on any asteroid that enters a resonant orbit. Instead of a gentle nudge, these regular gravitational kicks are cumulative. Over millions of years, they repeatedly perturb the asteroid's path, dramatically altering its orbit, making it more elliptical. This new, stretched-out path will eventually cross the orbits of other planets, leading to a close encounter that violently ejects the asteroid from the belt entirely, either flung inward toward the terrestrial planets or outward toward the gas giants. The Kirkwood gaps are therefore not empty because asteroids never formed there. They are empty because Jupiter's gravity has efficiently and permanently evicted any object that dared to settle into that rhythmic celestial dance. This phenomenon is a spectacular demonstration of gravitational harmony and chaos working in concert. It reveals our solar system not as a static collection of rocks, but as a dynamic, evolving system where gravity is a constant sculptor. The pattern of the gaps is a direct imprint of Jupiter's influence, a lasting signature of its role as the gravitational guardian of the inner solar system. In fact, many of the asteroids that get ejected from these gaps become the near-Earth objects we monitor today, and some are likely the source of meteorites that eventually fall to our planet. The Kirkwood gaps are a powerful reminder that even in a zone of apparent chaos, the underlying laws of physics can produce exquisite mathematical order. It shows that emptiness can be just as telling as presence, a silent testimony to the powerful forces that have shaped our cosmic neighborhood for over 4 billion years. This elegant interplay of gravity and resonance, so clearly illustrated in our own asteroid belt, now prepares us to look far beyond our solar system, where we find a similar theme of orbital harmony playing out on an even grander and more perplexing stage. Leaving behind the gravitational harmony of our own asteroid belt, we now journey far beyond our solar system to discover entire families of worlds orbiting distant stars, and here we find a pattern of cosmic order that is both beautiful and deeply puzzling. In many of these multi-planet systems, the orbits of the planets are not just stable, they are peculiarly, almost perfectly aligned. Imagine a star and around it, several planets all orbiting in the same flat plane, like grooves on a vinyl record. Their paths are coplanar, their movements synchronized in a graceful, flat disk. This is in stark contrast to our own solar system, which, while generally flat, has planets with orbits that are slightly tilted relative to each other, a relic of a more violent, chaotic formation history involving gravitational jostling and planetary migrations. These exoplanetary systems, with their exquisite alignment, suggest a far more serene and orderly birth. They appear to have formed from a calm, undisturbed protoplanetary disk of gas and dust, where planets coalesced gently and remained in the peaceful, flat plane of their original nursery without any major disruptive events to throw them into disorder. This precise orbital architecture challenges some of our key theories about how planetary systems evolve. The standard model of planet formation does predict that planets will form in a disk, but it also accounts for a significant amount of chaos. Giant planets like Jupiter are thought to have migrated inward from where they formed, a process that would have scattered smaller planets and severely perturbed the system's delicate alignment. The existence of these perfectly coplanar systems suggests that such dramatic migration may not be a universal rule. Perhaps some protoplanetary disks are simply more placid, or maybe the planets within them form and settle into their orbits with minimal interaction, preserving the pristine flatness of their primordial disk. This isn't just an academic distinction. It has profound implications for the habitability of any Earth-like worlds that might be present in these systems. A highly aligned system is likely to be dynamically stable over billions of years, providing a steady and predictable environment crucial for the long-term development of life. A chaotic system with crossing orbits and high orbital tilts would lead to frequent gravitational perturbations, potentially hurling promising planets out of their habitable zones or subjecting them to relentless bombardment, making the evolution of complex life far less likely. As we compare the serene order of these distant planetary systems to the relative chaos of our own, it forces us to reconsider our place in the cosmos. For a long time, we assumed our solar system was a typical example, Now we are learning that it might be an outlier, a product of a more dynamic and violent history. The discovery of these perfectly aligned exoplanetary systems expands our understanding of the possible pathways of planetary formation and reminds us that the universe can create both serene order and productive chaos. This contemplation of deep time and the gentle birth of worlds now shifts our perspective to an entirely different scale and a far more violent rhythm, as we encounter a temporal pattern that suggests our entire galaxy might be subject to a cycle of catastrophic upheaval, a pulse of destruction that may have repeatedly shaped the history of our own planet. This idea of a galaxy with a rhythmic, destructive pulse leads us to one of the most controversial and sweeping patterns ever proposed, the theory of galactic superwaves. Imagine our Milky Way not as a peaceful, stable island universe, but as a sleeping giant with a violent, beating heart, a heart that occasionally erupts, sending tsunamis of high-energy radiation and cosmic rays coursing through its spiral arms on a cycle that spans millions of years. This is the core of the galactic superwave hypothesis, a theory that suggests the supermassive black hole at the center of our galaxy, Sagittarius A, does not slumber quietly. Instead, it may experience periodic, explosive awakenings, perhaps due to sudden bouts of intense accretion or the destabilization of its surrounding magnetic fields. When this happens, it doesn't just burp, it unleashes a colossal shockwave that propagates outward at a significant fraction of the speed of light, a wall of energy that would fundamentally alter the environment of every star system in its path, including our own. The potential consequences of such an event for Earth are staggering to contemplate. As this wave of radiation passes through our solar system, it would dramatically compress the heliosphere, the protective magnetic bubble created by the solar wind that shields us from the worst of interstellar space. With that shield weakened, our planet would be suddenly and intensely exposed to a flood of galactic cosmic rays and high-energy particles. In the geological record, such an event might leave behind a distinct signature, a global layer of sediment enriched with rare isotopes like iron-60 and plutonium-244, which are forged in supernova and other violent cosmic events and could be deposited across the planet by such a wave. Proponents of the theory point to evidence of just such layers in deep sea and ice cores, suggesting timestamps that could align with past extinction events or major climatic shifts. The idea is that these cosmic radiation waves could act as a trigger, dramatically altering Earth's atmosphere, increasing cloud cover, sparking lightning storms, and potentially driving climate change severe enough to precipitate ice ages or mass extinctions. It's a grand, unifying theory that connects the violent core of our galaxy directly to the fate of life on our planet, proposing that evolution itself may have been periodically jolted forward or reset by these rhythmic catastrophes from the depths of space. It is crucial to note, however, that this theory remains highly debated within the scientific community. The primary challenge is the timescale. These events are proposed to occur every 10 to 15 million years, a span of time so vast that gathering conclusive, statistically significant evidence is extraordinarily difficult. The isotopic evidence, while intriguing, is not yet universally accepted as proof of a galactic-scale eruption, and other explanations, like the chance passage of our solar system through a nearby supernova remnant, are also plausible. Furthermore, the mechanics of what could cause such a periodic and titanic release of energy from our galaxy's core are not well understood. Despite these valid criticisms, the superwave theory endures because it dares to challenge a fundamentally static view of our cosmic environment. It forces us to consider that the galaxy is not a passive backdrop but an active, dynamic, and occasionally dangerous participant in the story of life on Earth. It suggests that the universe might not only create life through slow, steady processes, but could also occasionally administer a brutal, cosmic-scale selection pressure, a rhythm of catastrophe written on a million-year scale that we are only just beginning to perceive. And as we pull our gaze back from this sweeping vision of galactic cycles, we find a different kind of pattern, one not of time but of space, waiting for us just next door in our nearest major galactic neighbor. As we contemplate the grand, rhythmic cycles that might pulse from our galaxy's core, we now turn our attention to a much more intimate, yet equally profound, pattern much closer to home, one that is literally reshaping our understanding of how galaxies like our own are built. For decades, astronomers envisioned the vast halos of giant galaxies like Andromeda and the Milky Way as spherical clouds, within which dozens of smaller dwarf satellite galaxies would buzz about in a random, chaotic swarm like bees around a hive. This was a foundational prediction of our leading cosmological model, which posits that galaxies grow by gravitationally attracting and cannibalizing smaller neighbors over billions of years, with the surviving satellites ending up in a disordered, three-dimensional cloud. The reality, as we've now discovered, is startlingly different and far more elegant. When we map the precise positions and motions of the dwarf galaxies orbiting our nearest major galactic neighbor, the Andromeda Galaxy, we find they are not randomly scattered at all. Instead, they are organized with breathtaking precision into an immense, thin, rotating plane, a vast, disk-like structure that is both incredibly flat and coherently moving. It's as if these dozens of galaxies are all riding on the same colossal, invisible merry-go-round, circling Andromeda in a synchronized dance that defies the expectation of a chaotic halo. This discovery is not a minor curiosity. It is a direct and serious challenge to the standard model of galaxy formation. The sheer flatness of this structure and the coordinated motion of the dwarfs within it are extremely difficult to explain if these satellites are the leftover remnants of many different small galaxies that were independently captured by Andromeda's gravity over time. Such a random assembly process should have resulted in a much more spherical and disordered distribution. The existence of this rotating plane strongly suggests that these dwarf galaxies did not form in isolation. Instead, they likely share a common origin story, a coherent formation process that imprinted this organized motion upon them from the very beginning. One compelling theory is that they all formed together from a single, massive ring of gas and dark matter that was present in the early universe, perhaps a gigantic filament that was drawn into Andromeda's gravitational pull. As this structure collapsed, it could have naturally formed a rotating disk of protogalactic material, which then fragmented into the individual dwarf galaxies we see today, all preserving the original rotational motion of their parent structure. Another possibility involves powerful tidal forces. During a dramatic close encounter with another galaxy in the distant past, immense gravitational tides could have ripped out vast streams of material from Andromeda, and this ejected material could have later coalesced into new dwarf galaxies that inherited their ordered motion from the original tidal interaction. Perhaps the most intriguing aspect of this discovery is that it is not unique to Andromeda. A very similar, thin plane of satellite galaxies has also been identified orbiting our own Milky Way. This parallel finding transforms the pattern from a single anomaly into a potential universal feature of how giant spiral galaxies are assembled, forcing a major rethink of the entire process. The prevailing theory, which relies heavily on the random mergers of small systems within a dark matter halo, struggles to naturally produce such flat, rotating structures around two different galaxies. This has led some scientists to question whether our understanding of dark matter itself might need refinement. Perhaps dark matter has subtle properties that allow it to form these vast, pancake-like substructures more readily than our simulations predict. Or, in a more radical departure, it could be evidence that we need to modify our theory of gravity on galactic scales, though this remains a highly contested idea. Whatever the ultimate explanation, the dwarf galaxy plane around Andromeda stands as a majestic and humbling reminder that the universe often prefers beautiful, organized patterns over chaos, even on the grandest of scales. It shows us that the story of galaxy assembly is far from complete, and that our nearest cosmic neighbor holds vital clues to unlocking the secrets of our own galactic home. This contemplation of large-scale structure and motion now leads us to peer even deeper into the fabric of the cosmos, to a pattern so subtle and controversial that, if confirmed, could challenge the most fundamental pillar of modern cosmology, the very expansion of the universe itself. This concept of redshift is one of the cornerstones of modern cosmology. When astronomers look at the light from a distant galaxy, they often find its characteristic spectral lines are shifted toward the red end of the spectrum. This is interpreted as a Doppler effect, indicating the galaxy is moving away from us. Because we live in an expanding universe, the greater the redshift, the farther away the galaxy is and the faster it is receding. This relationship forms the basis for our entire cosmic distance ladder and our understanding of the universe's expansion history. It's a beautifully simple and powerful idea. But what if this fundamental tool, this bedrock of our measurements, was showing us something more complex and far more strange than we ever anticipated? This brings us to one of the most persistent and controversial patterns in all of astronomy, the claim that redshifts are not smoothly distributed, but instead are quantized, meaning they appear to prefer specific, discrete values like rungs on a cosmic ladder. The idea is as radical as it is simple. Instead of galaxies having all possible redshifts, and by extension all possible distances, the observations suggest they tend to cluster at certain specific values. It would be as if you were measuring the height of every person on Earth and found that they were only ever 5 feet, 5 feet 6 inches, or 6 feet tall, with no one in between. For the universe, this would imply that galaxies are not spread out continuously, but are organized on vast, concentric spherical shells centered on our own Milky Way. The preferred distances proposed are staggering in scale, with shells separated by intervals of roughly 200 million light-years. If true, this wouldn't just be a curiosity. It would be a direct challenge to the cosmological principle, the foundational assumption that the universe is homogeneous and isotropic, that it looks roughly the same in every direction and from every location. A quantized redshift pattern centered on us would suggest our galaxy holds a special, privileged position in the cosmos, a notion that modern science has thoroughly rejected since the time of Copernicus. The evidence for this phenomenon has been debated for decades, with some astronomers presenting compelling statistical analyses of galaxy surveys that appear to show these periodic peaks, while others dismiss the findings as an artifact of selection bias or flawed methodology. The central question is whether this is a real physical pattern in the universe or a pattern inadvertently imposed by the way we collect and interpret our data. Could it be that the way galaxies are distributed in great walls and filaments, the very structure of the cosmic web, is creating the illusion of periodicity in certain surveys? Or might there be subtle errors in how we calibrate our instruments or correct for the motion of our own solar system that could introduce a false signal? The scientific community remains deeply divided, and for good reason. The implications of quantized redshifts are so profound that the burden of proof is extraordinarily high. It would require nothing less than a revolution in our understanding of physics, potentially pointing toward a universe with a cellular structure, evidence of a multiply connected topology like a hall of mirrors on a cosmic scale, or even clues that the redshift itself is not entirely due to the expansion of space, but has another yet unknown component. Whether a monumental discovery or a monumental mirage, the very fact that this pattern is taken seriously enough to be debated for over half a century speaks volumes. It represents the ultimate scientific cautionary tale, reminding us to constantly question our most basic assumptions and our interpretation of the data. It forces a rigorous re-examination of the tools we use to measure the universe, ensuring we are not mistaking the fingerprints of our own methods for the handwriting of nature. And if by some chance this quantization is confirmed by future, more precise observations, it would open one of the most exciting chapters in the history of science, a complete rewrite of our cosmic address and our place in the grand scheme of things. This deep scrutiny of the very light we use to map the cosmos naturally leads us to another, equally brilliant mystery, one that doesn't question the meaning of the light's color, but its staggering, almost impossible intensity. While the mysterious quantization of redshift challenges how we measure cosmic distances, the universe offers another, far more violent and luminous puzzle that needs no such subtle interpretation. Imagine a stellar explosion so cataclysmic, so unimaginably energetic, that it outshines an entire galaxy, radiating with the power of hundreds of normal supernovae combined. These are not your typical dying stars, these are superluminous supernovae, and their existence pushes the very limits of what we thought was physically possible for a star to achieve in its final moments. A standard supernova is already one of the most powerful events in the universe, the spectacular death throes of a massive star or the detonation of a white dwarf. Yet, these extraordinary events leave even those in the dust, shining with a ferocious brilliance that defies all conventional models of stellar death. They are the cosmic equivalent of a bomb going off next to a firecracker, and their discovery has sent astrophysicists back to the drawing board to dream up new engines of destruction. The leading theory to explain these monstrous explosions involves the birth of an incredibly magnetic neutron star known as a magnetar at the heart of the blast. In a typical supernova, the core of a massive star collapses into a neutron star, and the gravitational energy released from this collapse powers the explosion that shreds the star's outer layers. But in the superluminous scenario, that newborn neutron star is spinning at an incredible rate and possesses a magnetic field trillions of times stronger than Earth's. This cosmic powerhouse acts like a massive dynamo, transferring its immense rotational energy into the expanding shell of stellar debris over a period of weeks or months. It's this continuous, central engine of magnetic fury that keeps the supernova shining brilliantly long after a normal explosion would have begun to fade, like pouring gasoline on a dying fire to create a sustained, dazzling inferno. Another compelling explanation for the very brightest of these events is a phenomenon called pair instability. This occurs in the most massive stars imaginable, those born with a core between approximately 130 and 250 times the mass of our Sun. In these stellar behemoths, the core temperature becomes so astronomically high that it begins to spontaneously convert energy into matter, creating pairs of electrons and their antimatter counterparts, positrons. This process is a catastrophic theft of the radiation pressure that was holding the star up against the crushing force of its own gravity. Without that internal support, the core collapses precipitously, triggering a runaway thermonuclear explosion that doesn't just blow off the star's outer layers. It completely annihilates the entire star, leaving behind no black hole or neutron star, just an expanding cloud of radioactive debris. The sheer amount of radioactive nickel-56 synthesized in such an event is staggering, and its decay is what powers the incredible galaxy-eclipsing luminosity. This is a true Titan's death, a final act of total self-immolation that is both beautiful and terrifying in its completeness. What makes the study of these events so crucial is that they are not just astronomical curiosities, they are cosmic signposts and chemical forges. Because they are so phenomenally bright, we can detect them at truly extreme distances, allowing us to probe the conditions of the early universe and measure its expansion rate independently of other methods. Furthermore, these explosions are the primary factories for many of the heavy elements that make up our world and our very bodies. The extraordinary conditions within a superluminous supernova likely produce a unique mix of elements, scattering them across interstellar space in vast quantities and seeding future generations of stars and planets with the building blocks of complexity. They are a stark and brilliant reminder that the life cycle of stars is far from a settled science. It is a field still ripe with discovery, where the universe continues to reveal new, more violent, and more spectacular ways for its largest inhabitants to meet their end. This profound realization that our understanding of cosmic energy and matter is still evolving sets the stage perfectly for our next mystery, which moves from the brilliant, visible aftermath of stellar death to the invisible, ghostly presence that governs the cosmos, the puzzling distribution of dark matter. This profound puzzle of light leads us directly to its polar opposite, the invisible enigma of dark matter. For decades, our most successful cosmological model, known as lambda cold dark matter, has painted a very specific picture of how this mysterious substance should behave. According to the theory, dark matter is cold, meaning its particles move slowly, and it doesn't interact with light or with itself. It only feels the force of gravity. Supercomputer simulations based on these rules have been incredibly successful at predicting the universe's large-scale structure, accurately forming the cosmic web of filaments and voids we observe. When these simulations zoom in on individual galaxies, they consistently generate a specific prediction. Each galaxy should be embedded within a vast, roughly spherical halo of dark matter, and the density of this halo should skyrocket toward the galaxy's center, forming an extremely dense, sharp cusp of dark matter. But the universe, it seems, has other ideas. When astronomers set out to measure the actual distribution of dark matter within real dwarf galaxies, small, faint galaxies that are dominated by dark matter, they found something startlingly different. Instead of a steeply rising density cusp, the observations consistently pointed toward a much shallower distribution, a core of roughly constant density that looks more like a soft, fuzzy ball than a sharp, dense peak. This isn't just a minor discrepancy, it's a significant and persistent tension between what our premier theory predicts and what we actually see in the sky. It's as if the simulations tell us to expect a towering, craggy mountain peak at the center of every galaxy, but our telescopes keep finding gently rolling hills. This Core-Cusp problem has become one of the most stubborn and intriguing anomalies in modern astrophysics, a direct challenge to the cold, collisionless nature of dark matter as we currently understand it. This glaring mismatch has forced scientists to consider some truly fascinating possibilities. The first is that our understanding of dark matter itself is incomplete. Perhaps dark matter isn't entirely cold and non-interacting. Maybe the particles can interact with each other through some unknown force, effectively bouncing off one another. This self-interaction would act like a form of friction, smoothing out the dense central cusp predicted by the simulations and creating the shallower cores we observe. It's a compelling idea, but it requires carefully tuning the strength of these interactions to match the data without disrupting the model's other great successes on larger scales. The second, and even more radical, possibility is that we don't need to invent a new type of dark matter at all. Perhaps we need to modify our understanding of gravity itself. Theories like modified Newtonian dynamics, or MUND, propose that gravity behaves differently at the very low accelerations found in the outskirts of galaxies. Intriguingly, MUND and its relativistic extensions can naturally explain the rotation curves of many galaxies without requiring any dark matter, and they often predict the kind of constant density cores that we observe. However, MUND struggles to explain the gravitational lensing effects of galaxy clusters without still invoking some form of dark matter, leaving the scientific community in a vigorous debate over which path is correct. This ongoing puzzle is far more than an academic exercise. It strikes at the very heart of how galaxies form and evolve. The distribution of dark matter sets the gravitational stage upon which the visible drama of stars and gas plays out. Getting it right is essential for understanding everything from the earliest moments of galaxy assembly to the final structure we see today. The Core-Cusp problem serves as a powerful reminder that our models, however successful, are always approximations of a more complex reality. It forces a humility upon us, demonstrating that the universe is still perfectly capable of presenting us with a fundamental mystery that resists our best efforts at explanation. This deep dive into the hidden architecture of individual galaxies now expands our view to an even larger canvas, prompting us to ask if the influence of dark matter, or perhaps a modified law of gravity, might also be responsible for orchestrating a pattern of motion on a truly cosmic scale. Now, if the coordinated motion of satellite galaxies hints at a local choreography, the next pattern expands this dance to a truly cosmic scale, revealing an alignment so vast it seems to orchestrate the very spin of the universe itself. Imagine looking out across hundreds of millions of light years and discovering that the rotation axes of countless galaxies are not pointing in random directions, as one might expect from a chaotic and random universe, but instead show a curious preference to align with each other, as if they were all compass needles responding to some immense, invisible magnetic field. This isn't about how they move through space, but how they spin. Their intrinsic angular momentum appears to be coordinated across volumes of space so enormous that the galaxies within them should have no way of communicating or influencing each other. This large-scale alignment of galaxy rotation axes is a profound and deeply puzzling pattern that challenges the very foundation of our cosmological principles. The standard model of cosmology is built upon the idea of isotropy and homogeneity, the assumption that the universe on its largest scales has no preferred direction and looks the same everywhere. This principle of cosmic mediocrity suggests there should be no special place or direction in the universe. The random, chaotic process of galaxy formation through mergers and collisions should, in theory, result in galaxies having rotation axes that are oriented completely randomly, like a vast crowd of people all spinning in place, each twirling in their own unique and unrelated direction. The discovery that there might be a significant statistical preference for these spins to align, therefore, strikes directly at this core assumption. It suggests that the initial conditions of the universe were not perfectly smooth and random after all, but may have contained subtle, large-scale patterns of spin, like a primordial whirl imprinted on the fabric of spacetime during the first moments of the Big Bang. This initial angular momentum could have been inherited by the collapsing clouds of gas that formed galaxies, locking in this preferred direction for billions of years. One compelling explanation for this eerie coordination involves the immense cosmic flows and the gravitational influence of the cosmic web. We know that galaxies are not stationary. They are pulled by gravity toward regions of higher mass density, flowing along the invisible filaments of dark matter that make up the universe's large-scale structure. It's possible that these vast rivers of moving matter, these coherent flows on scales of hundreds of millions of light-years, could have imparted a specific, shared sense of rotation to the galaxies forming within them. As protogalactic gas clouds collapsed, their spin could have been tidally twisted by the gravitational shear forces generated as they moved through these large-scale flows. In this scenario, the alignment wouldn't be a direct communication between mature galaxies, but rather a fossil record, a preserved signature of the dynamic environment in which they were all born together, a shared childhood experience written in the language of spin. The implications of confirming this pattern are staggering. If the spin axes of galaxies are truly aligned over such vast distances, it would provide a unique and powerful window into the very earliest moments of the universe, offering clues about the nature of cosmic inflation and the primordial quantum fluctuations that seeded all structure. It would suggest that the universe's initial state had a level of order and coherence that we are only beginning to appreciate. Furthermore, this large-scale alignment would be deeply interconnected with the mysterious nature of dark matter and dark energy, as the properties of these unknown components dictate how the cosmic web forms and evolves, which in turn would influence these massive flows that potentially shape galactic rotation. This pattern moves us from seeing galaxies as isolated islands to understanding them as integral parts of a dynamic, flowing cosmic ocean, their individual motions and spins deeply entwined with the largest structures in existence. This contemplation of immense, ordered flows naturally leads our inquiry to an even more precise and controversial measurement, one that searches for a hidden rhythm in the very fabric of cosmic expansion itself. This idea of a universe with a preferred structure, perhaps even a center, leads us to one of the most controversial and mind-bending patterns ever proposed, the suggestion that the redshifts of galaxies are not randomly distributed, but instead cluster at specific periodic values. Redshift is the key measurement astronomers use to gauge the distance of faraway galaxies. The more the light is stretched toward the red end of the spectrum, the faster the galaxy is receding from us due to the expansion of the universe, and therefore the farther away it is. This relationship is the very foundation of our modern cosmic distance ladder. But what if this fundamental tool was showing us something more complex than a smooth, ever-increasing gradient? Some analyses of large galaxy surveys have indicated that galaxies seem to prefer certain redshifts, appearing to be grouped at specific distances from us, as if they were arranged on a series of immense concentric spherical shells. The proposed scale of this pattern is almost incomprehensible, with shells potentially separated by intervals of hundreds of millions of light-years. If this pattern is real and not a statistical fluke or an artifact of how we sample the data, the implications are nothing short of revolutionary. It would directly challenge the cosmological principle, a cornerstone of modern astronomy, which states that the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction and from every location, with no special place or center. A periodic redshift distribution centered on our Milky Way would, by definition, place us at the center of this cosmic architecture, a profoundly un-Copernican idea that science has resisted for centuries. This has led to intense debate within the astronomical community. Skeptics argue that the apparent periodicity is likely an illusion, a consequence of the way galaxies are naturally clustered into the vast filaments and walls of the cosmic web, which can create peaks and troughs in distance measurements that might mimic a regular pattern when viewed from a certain perspective. It could also stem from subtle biases in our observation techniques or the challenges of correcting for our own solar system's motion through the galaxy. Yet, for those who argue the pattern is genuine, the explanations venture into extraordinarily speculative and fascinating territory. One compelling possibility is that it reveals the universe is not infinite and simply connected, but instead has a multiply-connected topology. Imagine the universe is not like an endless flat plane, but more like a video game world where if you travel far enough in one direction, you eventually return to your starting point, a structure known as a torus or perhaps a more complex shape. In such a finite universe, light could wrap around on itself, and we might be seeing the same galaxies or the same large-scale structures repeated at different distances, creating the illusion of a lattice of shells. This would mean our observable universe is actually a repeating pattern, a cosmic hall of mirrors on an unimaginable scale. Confirming this would radically alter our cosmic perspective, transforming our universe from a vast, unknowable expanse into a defined and potentially mappable geometric shape. Whether a profound truth about the cosmos structure or a persistent mirage in our data, this pattern forces a rigorous re-examination of our most fundamental assumptions and reminds us that the universe is always capable of surprising us with a deeper layer of order. From this grand speculation about the topology of all reality, we now turn our attention to a pattern that hits much closer to home, one written not in the light of distant galaxies, but in the fossilized bones of our own planet's history, suggesting a rhythmic pulse of destruction that may have celestial origins. This journey from the vast architecture of the cosmos now brings us home to a pattern written not in starlight, but in stone and bone, a rhythmic pulse of destruction etched into the very fossil record of our planet. For decades, paleontologists have meticulously documented the history of life on Earth, and a startling pattern has emerged from the data. Mass extinction events, where a significant percentage of all life is wiped out, appear to occur with a rough periodicity of about 26 to 30 million years. This is not a random series of catastrophes. It is a chillingly regular beat, a metronome of death that has punctuated the evolutionary saga at least 5 times over the last 500 million years. The most famous of these events, the one that claimed the dinosaurs 66 million years ago, was long thought to be a singular freak accident, a lone asteroid impact. But the emerging pattern suggests this was not an isolated incident. It was merely the most recent tick of a cosmic clock, the latest chapter in a cyclical narrative that connects the fate of all life on Earth to the grand motions of our solar system through the galaxy. The search for a mechanism behind this rhythm leads us directly from the geology of our planet to the celestial dynamics of our galactic neighborhood. The most compelling theory involves a distant yet unseen companion to our Sun, a hypothetical small, dim star or brown dwarf nicknamed Nemesis. In this model, Nemesis would orbit the Sun on a wide, elliptical path that brings it through the icy outer reservoir of our solar system, the Oort cloud, every 26 million years or so. Its gravitational passage would act like a shepherd stirring a flock, dislodging countless comets from their stable orbits and sending a shower of these icy bodies hurtling inward toward the Sun and on a collision course with Earth. This periodic bombardment would rain down devastation on a global scale, triggering a cascade of effects, impact winters, global wildfires, and dramatic shifts in climate that would collapse ecosystems worldwide. While evidence for Nemesis remains elusive, the mathematical elegance of the idea provides a powerful potential link between a hidden celestial dance and the cycles of life and death on our planet. An alternative, and perhaps even more grand, cosmic explanation involves the motion of our entire solar system as it orbits the Milky Way. Our galaxy is not a flat disk, It has a slight warp, a wobble, and our Sun doesn't orbit in a perfect plane. Instead, it oscillates up and down, crossing the crowded mid-plane of the galactic disk approximately every 30 to 35 million years. Each time we pass through this densest region of the galaxy, the gravitational environment around our solar system becomes significantly more chaotic. The increased density of stars and interstellar gas clouds could perturb the Oort cloud just as effectively as a hypothetical nemesis, triggering another shower of comets. Furthermore, passing closer to other stars could directly fling asteroids from the main belt into Earth-crossing orbits. This theory beautifully situates our planet's biological history within the broader context of galactic mechanics, suggesting that the rise and fall of species are intimately tied to our journey through the Milky Way. This interdisciplinary fusion of astronomy and paleontology fundamentally challenges an Earth-centric view of history. It argues that the most pivotal events shaping the evolution of life are not solely the result of volcanic eruptions or climate shifts originating on our own planet. Instead, they are often orchestrated by forces of an immense and impersonal cosmic clockwork. The pattern of cyclical extinctions suggests that evolution is not a slow, steady, continuous process, but a punctuated equilibrium, repeatedly reset by external astronomical triggers. These catastrophic events, while devastating, also create ecological opportunities, clearing the way for new life forms to explode into the vacated niches. In a very real sense, we mammals owe our dominance on Earth to one of these cosmic interventions that ended the reign of the dinosaurs. This realization reframes our place in the universe. We are not isolated on a safe, stable world, but are passengers on a planet that is itself moving through a dynamic and occasionally dangerous galactic environment. As we contemplate this rhythmic exchange of energy between the cosmos and our biosphere, it primes us to examine another, far more energetic imbalance, one that occurs in the largest gravitationally bound structures in the universe. But if the cyclical rhythms of mass extinctions connect Earth's biological history to the grand motions of our galaxy, the next pattern reveals a profound energetic imbalance at the very heart of the universe's largest structures. Galaxy clusters are the titans of the cosmos, immense cities of thousands of galaxies all bound together by gravity and swimming in a vast, seething ocean of superheated gas. This intracluster medium is unimaginably hot, reaching temperatures of tens of millions of degrees, so energetic that it shines not in visible light, but in powerful X-rays. For a long time, our understanding of these clusters was beautifully simple. They should be like a pot of water on a stove that's been turned off. The dense core, where most of the mass congregates, should naturally be the hottest region due to the immense gravitational pressure. However, if you leave that pot of water alone, the hottest part will eventually cool down as the heat radiates away. In the same way, the super-hot gas in the very center of a cluster should gradually lose its energy, cooling and condensing, and then funneling down to feed the central galaxy, triggering tremendous bursts of star formation. This is known as cooling flow theory, and it makes perfect intuitive sense. The universe, however, has a habit of defying intuition. When astronomers pointed their most powerful X-ray telescopes, like Chandra, at the cores of these clusters, they found something completely unexpected. The gas in the very centers was indeed incredibly dense, but it wasn't cooling down as much as it should have been. In fact, it remained stubbornly hot, preventing the predicted deluge of condensing gas and star formation. It was as if that pot of water on the stove was staying boiling hot in the center, despite constantly radiating heat away, implying that some hidden flame was still burning underneath it. This cooling flow problem meant our models were missing a crucial piece of physics. Something was actively reheating the cluster cores, injecting vast amounts of energy to offset the relentless radiative cooling and maintain this anomalous, sustained heat. The prime suspect in this cosmic reheating mystery is the most energetic engine in the universe, the supermassive black hole lurking at the center of the cluster's dominant galaxy. When gas does manage to cool and fall toward this black hole, it doesn't go quietly. The black hole erupts, transforming its gravitational feast into a monstrous outpouring of energy. It does this by launching colossal jets of plasma, moving at nearly the speed of light, that punch far out into the intracluster medium. These jets inflate giant bubbles of radio-emitting gas that act like cosmic pistons, creating shock waves that travel through the cluster's atmosphere, stirring and heating the gas in a process known as AGN, or active galactic nucleus feedback. It's a spectacular self-regulating cycle. As the cluster gas cools, it feeds the black hole, which then erupts and heats the gas back up, shutting off its own fuel supply. This feedback loop is a masterpiece of cosmic engineering, a balancing act that prevents the cluster from either overheating or collapsing into a frenzy of star formation. It's a stunning example of how the very largest structures in the universe can be governed by the very smallest and most extreme objects within them. Yet, even the formidable energy output from these supermassive black holes might not tell the whole story. Some scientists have proposed an even more exotic secondary heat source lurking within these scorching cores, the annihilation of dark matter. The theory suggests that if dark matter particles are their own antimatter counterparts, they could annihilate upon collision, converting their mass directly into energy. In the incredibly dense center of a galaxy cluster, where the concentration of dark matter is at its peak, the rate of these collisions could be high enough to provide a significant and steady source of heat. This would be a faint, ubiquitous warmth emanating from the very heart of the dark matter halo itself, a constant background heating that works in tandem with the more violent, episodic outbursts from the central black hole. While this remains a highly speculative idea, it highlights how these anomalous hot cores are forcing us to consider every possibility, from the well-established physics of plasma jets to the frontier science of particle dark matter, all in our effort to balance the energy budget of the universe's greatest metropolises. This investigation into a surplus of heat and energy in the largest structures now turns our attention to a puzzling absence, a missing ingredient in the oldest stars that leaves a chilling gap in our story of the cosmos's origin. From the immense, searing heat of galaxy cluster cores, we now turn our attention to a much colder, more fundamental problem, one that involves not an excess of energy, but a puzzling absence of a specific element that should be there. This mystery is written in the faint light of the most ancient stars in our galaxy, and it challenges our understanding of the very first minutes of the universe's existence. According to our meticulously crafted models of Big Bang nucleosynthesis, the frantic few minutes following the birth of the cosmos should have produced a very specific primordial soup of light elements. Hydrogen and helium made up the vast majority, but the process also forged a tiny yet calculable amount of lithium. We can precisely predict how much lithium-7 should have been created in that initial cosmic furnace. This prediction is a cornerstone of our standard cosmological model, and for the most part, the predicted abundances of hydrogen and helium match what we observe in the oldest regions of the universe perfectly. But when it comes to lithium, the numbers simply don't add up. Astronomers measure the composition of ancient stars, known as population Roman II stars, which formed from nearly pristine gas early in the galaxy's history. These stellar relics act as cosmic time capsules, preserving the chemical makeup of the universe from a time before successive generations of stars had a chance to forge and scatter heavier elements. When we analyze their atmospheres using spectroscopy, we find that the amount of lithium is about 3 times lower than what our Big Bang calculations insist should be there. This isn't a small margin of error, it's a glaring discrepancy that has persisted for decades, stubbornly resisting every attempt to explain it away. It presents us with a stark choice. Either our understanding of the nuclear physics in the universe's first 3 minutes is incomplete, or our comprehension of the internal workings of the oldest stars is fundamentally flawed. The search for a solution has taken physicists and astronomers down 2 very different, yet equally fascinating paths. The first possibility is that our models of stellar astrophysics are missing a key piece of the puzzle. Perhaps these ancient stars have some unknown mechanism for destroying lithium deep in their interiors over their multi-billion-year lifetimes. Stars are not static objects, they have complex circulatory currents. It's possible that surface material, bearing its original lithium, gets dragged down into the hotter inner regions where temperatures are high enough to break the fragile lithium nucleus apart, effectively burning it as fuel. The processed, lithium-depleted material could then be brought back to the surface, masking the star's true primordial abundance, while models can produce some mixing. Creating enough of it to account for the factor of 3 discrepancy has proven to be a significant challenge. The second and far more profound possibility is that the error lies not with the stars, but with our particle physics. The predictions of Big Bang nucleosynthesis are exquisitely sensitive to the conditions of the early universe and to the fundamental properties of subatomic particles. Could there be an unknown type of particle, perhaps a candidate for dark matter, that was present in those first moments and interacted with nucleons in a way that suppressed the production of lithium? Or might there be an error in our measured cross-sections, the probabilities of certain nuclear reactions occurring that we have always taken for granted? This path of inquiry leads us to the thrilling, albeit unsettling, prospect that the lithium problem is not an astronomical curiosity, but a direct window into new physics beyond the standard model, a clue to forces or particles that played a role in shaping the universe's infancy. This missing lithium, a small detail in the grand scheme of cosmic chemistry, serves as a powerful and humbling reminder. It shows that even our most successful and well-tested theories can harbor unresolved contradictions. It underscores that the universe is a complex system, and that processes occurring over billions of years inside stars can obscure the signals from the universe's first few minutes. This puzzle of a missing ingredient in the oldest stars now shifts our focus from the chemical composition of the cosmos to its dynamic motions, as we explore a pattern that defies the standard direction of things, the curious phenomenon of retrograde motion in our own solar system. This consistent direction is a beautiful signature of the solar system's origin from a single, spinning cloud of gas and dust, a shared inheritance of motion. But as with any family, there are rebels, members that defiantly move against the grain. These are the celestial bodies with retrograde motion, spinning or orbiting in the exact opposite direction to the rest of their kin, and their existence tells a story of a far more violent and dynamic cosmic history than a simple, peaceful collapse could ever provide. The most stunning example of this backward behavior is the planet Venus. While every other planet in the solar system rotates counterclockwise as seen from above the Sun's north pole, Venus rotates clockwise. A single day on Venus, one full rotation, lasts longer than its entire year. This is a profound anomaly. The leading theory to explain this backward spin points to a catastrophic collision in the distant past. Imagine a protoplanet, a massive world in the making, slamming into a young Venus with such incredible force that it literally stopped the planet's original rotation and sent it spinning the other way. The immense torque of such an impact could have completely reversed its spin axis, leaving it with the slow, retrograde rotation we see today. It's a testament to the incredible violence that shaped the early solar system, a time when giant collisions were not just possible but commonplace. But the rebellion isn't confined to planets. Look at the moons of the gas giants, and you'll find several that are also marching to the beat of their own drum. Perhaps the most famous is Triton, the largest moon of Neptune. Triton doesn't just have a slightly tilted orbit, it orbits Neptune backwards or retrograde, moving in the opposite direction to the planet's own rotation and opposite to the orbit of every other large moon in the solar system. This is a giant red flag that Triton was not born alongside Neptune. An object of its size simply could not form in a stable retrograde orbit from the same material that formed the planet. The only logical explanation is that Triton was an independent traveler, a rogue object from the distant Kuiper belt that ventured too close to Neptune's gravitational influence and was captured. This capture event would have been incredibly dramatic, likely involving a complex gravitational dance with a binary partner that was ejected into deep space as Triton was forced into its new, backward orbit around the ice giant. Its capture also helps explain its fascinatingly active surface of nitrogen geysers. The tremendous tidal forces exerted during its capture and subsequent circularization of its orbit would have heated its interior for eons, providing the energy for ongoing geological activity. These retrograde motions are far more than just celestial curiosities. They are forensic evidence. They are the lingering scars and trophies from the solar system's most chaotic and formative era. The standard, orderly narrative of planetary formation is correct in its broad strokes, but it is these glorious exceptions that complete the picture, revealing a history punctuated by unimaginable collisions, gravitational hijackings, and chaotic interactions. They remind us that our cosmic neighborhood was not always the stable, clockwork system we see today. It was a violent construction zone where the rules were often broken, and the outcomes were as much about chance encounters as they were about fundamental physics. These backward spins and orbits are the enduring signatures of that chaos, a permanent record of the dynamic processes that ultimately crafted the diverse family of worlds we call home. And from this exploration of chaotic, backward motion that reveals a violent history, we now turn to a final pattern that represents almost the exact opposite, a breathtaking, serene, and perfectly symmetrical death. And from this exploration of chaotic, backward motion that reveals a violent history, we now turn to a final pattern that represents almost the exact opposite, a breathtaking, serene, and perfectly symmetrical death. In the final act of a star's life, when a sun-like star exhausts its nuclear fuel, it doesn't go quietly. It undergoes a spectacular transformation, shedding its outer layers in a beautiful, often intricate, cosmic shroud of glowing gas called a planetary nebula. For a long time, astronomers believed they understood the mechanics behind these stunning structures. As the dying star's core collapses into a white dwarf, it unleashes powerful stellar winds. Meanwhile, the intense ultraviolet radiation it emits ionizes the ejected material, making it glow. The prevailing theory suggested that most planetary nebulae should be bipolar, shaped like an hourglass, a butterfly, or even more complex forms. This asymmetry was thought to arise from the star's rotation, the presence of a magnetic field, or the gravitational influence of a binary companion star, all of which would focus the outflows into opposing jets, creating the classic two-lobed structure. But the universe, in its infinite creativity, had a surprise in store. Scattered throughout the galaxy are planetary nebulae that defy this expectation with an almost perfect, stunningly spherical symmetry. The most iconic example is Able 39, a vast, ghostly orb of glowing gas located about 7,000 light-years away. It is nearly a perfect circle, a celestial soap bubble floating in the void. This presents a profound puzzle. How does a sphere, the most symmetric shape possible, emerge from the complex, chaotic, and often asymmetrical process of stellar death? If bipolar shapes are the rule, then these perfect spheres are the magnificent exception that challenges the rulebook itself. The existence of these symmetrical wonders forces a re-evaluation of the final stages of stellar evolution. One compelling explanation is that the central star in these systems might have an unusually slow rotation or a very weak magnetic field. Without these forces to break the symmetry and channel the outflow into jets, the star's final breaths could be expelled evenly in all directions, like a perfectly spherical balloon inflating in the vacuum of space. Another fascinating possibility involves the delicate timing and interaction of stellar winds. A star doesn't eject all its mass at once. It goes through phases, emitting a slower, denser wind first, followed by a faster, lighter wind later. If these two winds interact in just the right way, if the fast wind catches up to and plows into the slow wind with uniform pressure from all sides, it can sculpt the expanding shell into a perfect sphere, shock heating the gas and causing it to glow with that characteristic ethereal light. Perhaps the most intriguing theory, however, involves the hidden hand of a binary companion. It might seem counterintuitive that a second star could create perfect symmetry rather than destroy it. But if the companion is very close to the dying star, its gravitational influence could actually help to stabilize the system, regulating the mass loss and preventing the instabilities that typically lead to asymmetric outflows. In this scenario, the binary pair acts as a single, coherent central engine, whose combined gravitational field can, under the right conditions, orchestrate a beautifully spherical ejection. Each of these explanations points to a more nuanced and complex picture of stellar death than we previously held, showing that the final form a star takes is exquisitely sensitive to its initial mass, its rotation, its magnetic personality, and its social life, whether it lived and died alone or with a partner. Able 39 and its spherical cousins are more than just pretty pictures. They are cosmic diagnostics. Their simple, symmetric shape acts as a perfect laboratory for astronomers. Because the gas is distributed so evenly, scientists can use it to accurately measure the chemical composition of the material ejected by the star, which is crucial for understanding how stars seed the galaxy with the heavy elements necessary for planets and life. Furthermore, the pristine geometry allows for precise studies of the physical conditions within the nebula itself, such as temperature and density gradients, free from the complicating factors of a chaotic structure. In their serene, circular perfection, these nebulae embody a profound cosmic truth, that the end of one thing can be the beginning of something of immense beauty and order. They are a final, peaceful note in the violent symphony of a star's life, a lasting monument to the elegant physics that can govern even the process of dissolution, proving that in the vastness of space, death can be as breathtakingly beautiful as birth. Having journeyed through these 25 cosmic enigmas, from the gravitational pull of the Great Attractor to the perfect spheres of dying stars, a profound truth emerges. These are not merely isolated curiosities, they are a collective symphony of anomaly, each note challenging a different assumption about the cosmos, and in doing so, reshaping the very foundations of astronomy and our philosophical view of reality. They force a humbling recognition. Our current models of the universe, however elegant and successful, are incomplete sketches of a far grander and more mysterious masterpiece. This constant state of being proven wrong is not a failure of science, it is the engine of its progress. Each unexplained pattern is a beacon, guiding us toward a deeper, more nuanced understanding, pushing the boundaries of physics into uncharted territory where new particles, new forces, or even new laws of nature might be waiting to be discovered. This relentless pursuit of answers to these cosmic riddles has a remarkable side effect. It drives technological innovation at a breathtaking pace. Consider the tools we've had to invent just to peer into these mysteries. To see through the zone of avoidance and study the Great Attractor, we developed telescopes that see in infrared and radio wavelengths. To map the subtle patterns in the cosmic microwave background with exquisite detail, we launched satellites like Planck into the frigid void of space. To catch the fleeting milliseconds of a fast radio burst, we built arrays of radio dishes that can scan the entire sky with incredible speed and precision. The need to simulate the vast cosmic web or the chaotic formation of planetary systems has pushed supercomputing to its limits, leading to advances in processing power and algorithms that ripple out into other fields. The quest to understand these patterns doesn't just satisfy curiosity, it forges the very instruments that expand our sensory reach into the universe, turning once impossible questions into routine science. Beyond the physics and the technology, these patterns stir deeper, more philosophical questions about our place in the cosmos. The eerie alignment of quasars over billions of light years, the potential periodicity in mass extinctions, and the suggestion of a quantized universe all challenge the Copernican principle, the idea that we do not occupy a special or privileged place in the universe. What if, on some level, we do, not in a preordained anthropocentric sense, but perhaps as observers situated in a unique position to witness a specific, fractal slice of a reality that might be structured in ways we are only beginning to glimpse? These anomalies force us to confront the nature of reality itself. Is the universe fundamentally mathematical, as the Fibonacci spirals of galaxies and the harmonic resonances of orbital gaps suggest? Or is it a place of inherent, beautiful chaos, where order is fleeting and emergent, as seen in the violent captures that create retrograde orbits? The search for answers blurs the line between science and philosophy, inviting us to ponder whether the cosmos is a cold, mechanistic clockwork or something more nuanced, more creative, and more wonderfully strange. Ultimately, this grand tapestry of cosmic mysteries serves as the ultimate testament to the human spirit of inquiry. It demonstrates that skepticism, the refusal to accept a comfortable answer simply because it's widely held, is as crucial to discovery as the curiosity that sparks the question in the first place. Every one of these 25 patterns began with an astronomer or a team of them looking at the data and having the courage to say, "This doesn't make sense." That willingness to sit with discomfort, to embrace the unknown, and to relentlessly pursue an explanation is what propels us forward. It reminds us that the universe is not a puzzle to be solved, but a mystery to be explored, an endless frontier that will always have new wonders to reveal to those who are willing to look up and question everything they think they know. We've traveled from the hidden gravitational might of the Great Attractor to the perfect geometric death of distant stars, exploring 25 cosmic patterns that defy simple explanation. Each one of these mysteries, from the synchronized dance of satellite galaxies to the rhythmic ticking of deep space radio bursts, does more than just puzzle scientists. It deepens our awe for the universe's boundless creativity and complexity. These aren't errors in our data or gaps in our understanding waiting to be filled. They are invitations to look deeper, think bigger, and question the very frameworks we use to make sense of the cosmos. They remind us that the universe is not a static picture to be analyzed, but a dynamic, evolving story that we are only just beginning to read. This journey underscores a beautiful truth about science. It is not a collection of facts, but a continuous process of wonder. Every time we think we have the answers, the cosmos presents us with a new question, a new pattern that challenges our perception and pushes the boundaries of what we believe is possible. This isn't a sign of failure, it's the engine of discovery. It means the universe is far more interesting, far more strange, and far more magnificent than we could ever imagine from our small corner of space. So the next time you find yourself under a clear night sky, take a moment to simply look up. Remember that within that vast expanse are forces and formations beyond our current comprehension, patterns of energy and matter that are waiting for the next curious mind to unravel them. Your curiosity is what drives this exploration forward. What was your favorite cosmic pattern from our list? Was it the mathematical perfection of Saturn's hexagon, or the mind-bending possibility of the CMB Cold Spot being a bruise from another universe? Share your thoughts and questions in the comments below. I love hearing what sparks your sense of wonder. If you enjoyed this deep dive into the universe's greatest mysteries, make sure to subscribe and hit the bell so you don't miss our next journey to the edges of understanding. Until then, keep looking up, stay curious, and never stop exploring. The universe is filled with patterns waiting to challenge and expand our perception, and the next great discovery